All right, so to drive home this quotient rule thing one last time, I wanted to take a look at an example in one of our applied contexts. In particular, we want to find an equation for a tangent line to this particular graph. So y equals 2x, over the quantity x plus 1, at a point with an x coordinate of 1. So to get the corresponding y value, you plug those guys in here, you get 2 over 2. So yeah, I'm trying to be friendly to you in that sense at least. Like the point's not that challenging. So we got our point. What's the other thing we need for a line's equation? That's right, we need a slope. And since it's a tangent line, we've seen through our buddy the circle of calculus, m is the same thing as our derivative value at x equals 1, which means we kind of need to get y prime of 1, so to speak. I didn't write it like it's a function of x, but you get the idea. So y prime. So now, since this is in fact a quotient, we need to use our buddy the quotient rule again. So yep, the old f up top, g down below setup. So we have x plus 1 quantity squared. Top side we will have f prime, that's 2, times g left by itself, so x plus 1, minus f without a derivative, so we have 2x, times the derivative of our denominator, which in this case is just 1. We actually had an x plus 1 denominator in the last example. I probably should have mixed that up. Whatever. All right. So now, if we clean this thing up, it actually cleans up rather nicely, I think you'll end up observing, because up top we get 2x plus 2 minus 2x, so we just have 2 in the numerator by its lonesome. Down below, we have x plus 1 quantity squared. Awesome. Now, to get our slope, we just plug x equals 1 into this thing. So we have 2 over 1 plus 1 squared. And last I checked, 1 plus 1 is 2, 2 squared is 4, 2 over 4 is just a nice, neat 1/2. So there's our slope. Now we have our slope, we have our point. So our line's equation is going to be y minus our y coordinate, y minus 1 equals our slope of 1/2 times x minus our x coordinate, also 1. So we've got y minus 1 equals 1/2 times the quantity x minus 1. You want that in slope-intercept form. I know web work is really big on making sure you've got like y equals and then a blank for the thing like in slope-intercept. We get what? 1/2 x minus 1/2 plus 1 should be plus 1/2 right there. So that was what I got previously. So yay me. So there's my tangent line equation. All right. So there's one example. Again, I like stressing the whole tangent line thing because it's something that's easy to overlook, but it's a good baseline for why we want to do this kind of stuff. So I want to take a look at one more example that's coming from a slightly different direction. So give me just a sec here. So this last example I want to take a look at, it almost ends up feeling a little bit more like what you might encounter like in a laboratory setting, because in those instances you might not necessarily have a formula for a derivative. You probably ended up doing like some lab observations and done some sort of chicanery to end up with numerical values for functions and derivatives at a certain point. So what I've got here is a couple of functions, cobbled together. I just called them f and g for simplicity's sake. And we know what their values are for an x coordinate of 5. So f of 5 is 1, f prime of 5 is 6, function value, derivative value, okay? G of 5 is -3, note the negative, also no derivative here, just a function value. And then lastly, G prime of 5 is 2. So like I said, these are the sorts of things that might come up if you were working out, like, say, velocities or something like in a physics lab, where you end up, using observations to determine, what's going on as like a block slides down a plane. Not to take anything away from your physics professor when the time comes. Hopefully, it won't feel like I've stolen their thunder. Anyway, so now we want to work out the values of some derivatives for these things at that same point. So if we had fg prime of 5. Again, so fg is just like the function you get by multiplying f and g together. So we might not have used that notation a bunch, but hopefully it seems intuitive. So fg prime of 5. So now what will often end up happening is students will get a little over, excited about this, and they'll say, hey, wait, these things are all constants. What's the derivative of a constant? It's 0. So they'll just write like a big 0 right here and feel very proud of themselves until, I happen to walk by their desk or I look at their paper and I say, oh no, you got to dig a little deeper than that. The idea here is we need to invoke the product rule on this thing. So it's going to look like, f prime of 5 times g of 5. Yeah, so like I said, the way the product rule set up, the whole, hoodie high, you remember that. I'm not going to repeat it again. So we have that guy right there. Now we can fill in our numerical values that we've done painstaking research or had teaching assistants do for us or whatever. Again, you get the idea. So f prime of 5 we said is 6. G of 5 is -3, so we have 6 times -3 for that first beast. F of 5 is 1. G prime of 5 is 2. And so now it's just arithmetic from here, right? So 6 times -3 is -18. 1 times 2 is 2. You add them together. And I think I should get a derivative value for that product of -16. So not 0, right? -16 is not the same thing as 0. All right, same deal. What if we had a quotient? So f over g prime. I think I tried to write another parenthesis there. I have no idea. Anyway, same deal. We invoke the quotient rule. We'll just have to fill in the blanks. So we have f prime of 5, g of 5, minus f of 5, g prime of 5. So again, instead of x, we have a specific x value, but that doesn't mean that everything's a constant. And then all over g of 5 squared. I'm in dire peril of running out of board space here, so I'm going to, try to collapse this down. So we have 6 times -3 again for this first bit, so we get -18 out of that guy, minus, now over here we still have f of 5, g prime of 5, so 1 times 2 again, but now it's got a minus on it, so it's -18 minus 2. And then underneath, g of 5 was -3. So we have -3, and that's squared. So when I work this out, if I'm doing all of my arithmetic right, and I'm pretty sure, you're hoping your math teacher can do arithmetic right. Yes, that's the goal. So I'm getting -20 up top and just +9 down below because negative times negative, you know that score. So that's what our derivative for our quotient would look like at x equals 5. Again, this all falls apart if we're working around a different, x value. If we wonder what's happening at, say, x equals 1 or, x equals 10, we need to do more observations to get the right numbers to go in those spots. All right, so that's the product and quotient rules. So yeah, that's that. We'll be moving on to another section of material on derivative processes. And we're going to dig into that one, way to combine functions that always kind of ends up, tossing us for a loop. So stay tuned.